In this segment, we're going to go over radioactivity. The most accurate way to find the age of a rocky body is to bring a sample into the laboratory and analyze the radioactive elements it contains. By radioactive, we mean the gradual decay of elements into other elements. For example, let's look at potassium-40. Potassium-40 is the parent isotope. Potassium gradually decays into calcium-40 and argon-40. Both calcium-40 and argon-40 are the daughter isotopes. Half-life is the time required for half of the atoms in a radioactive sample to decay. That is, the time it takes for half of the parent isotope to decay into the daughter isotope atoms. So over time, the abundance of the radioactive substance gradually decreases as it decays, and the abundance of the daughter substances gradually increase. For example, the half-life of potassium-40 is 1.3 billion years. Here's a graphical representation of half-life. The parent isotope is colored red, and the daughter isotopes are colored blue. On the horizontal axis, we're looking at time, where time starts at 0 on the left and increases to the right. On the vertical axis, we're looking at percent, where 0% is at the bottom and 100% is at the top. So at time t equal to 0, we have a rock that has 100% of the parent isotope in it. And then over time, some of that parent isotope decays into daughter isotopes. This particular rock has half of the parent isotope and half of the daughter isotope. In other words, half of the parent isotope is still remaining. Therefore, we would say that only one half-life has occurred. Remember the definition of half-life. It's the time required for half of the radioactive atoms, in other words, the parent atoms, to decay. So let's say you studied this rock right here, and that rock you're looking for the potassium-40 in the rock. Let's say you analyze the rock and you see only 1/2 of potassium-40, and the other half is a mixture of the daughter isotopes. Since only half of the potassium-40 are remaining, you would conclude that only one half-life has occurred. And since we know the half-life of potassium is 1.3 billion years, then one half-life times 1.3 billion years, that's equal to 1.3 billion years. And that would be the age of the rock. You will conclude that the rock is 1.3 billion years old. Now technically, this rock is not a rock at all. It's actually a meteorite. And this meteorite is 4.56 billion years old. It contains a few stellar grains that's even older than our solar system. Let's look at another example. Let's say you analyze this rock and it's got 1/4 potassium-40, which is radioactive, and it has 3/4 of a mixture of the daughter isotopes. You want to find out how old is the rock. Well, you analyze the situation. You've got 1/4 parent and you have 3/4 daughter. You analyze your figure and you see that your figure matches this figure. And if you follow the line down, that would be the number 2. 2 half-lives have occurred. So you know that the age of the rock is a multiplication of the number of half-lives, which is 2. And you know the conversions for potassium-40 is 1 half-life is equal to 1.3 billion years. So we multiply it out. 2 times 1.3 on the top, half-life drops out. So we're left with the unit of billions of years. And then on the denominator, we just see the number 1. So 2 times 1.3 billion years is 2.6 billion years. So you would conclude the age of the rock is 2.6 billion years old.